Let's talk about multiple regression. We've gone through a fairly extensive review of simple regression in which we have one quantitative response variable and one quantitative explanatory variable. Multiple regression is an extension where we now have multiple explanatory variables, not just one. This states that the regression line models the relationship among multiple explanatory variables and one response variable. Actually, let's just say regression models, because this actually shouldn't be line, it should be a regression plane. And what I mean by that is if you think about having, say, 3 variables, a y and 2 x's, you would have x going as an axis in one direction, x1, x2 going as an axis perpendicular to that, and y going as an axis perpendicular to that. So it would be 3 dimensions, and you would try to fit a plane through that. But that's a little bit more than I want to take on right now. There actually is a way that we can get a line out of that. It has to do with looking at the relationship of our predicted and observed values. But let's go ahead right now and just say regression models the relationship among multiple explanatory variables. We won't think of it graphically right now. We'll just think about regression modeling the relationship among multiple explanatory variables and one response variable, and we can think of that in terms of an equation like you see here. So I have one response variable. The outcome that I observe is y. I have multiple explanatory variables. There's one, x1, x2, x3, x4, all the way up to xp, where p here is the number of variables, the number of explanatory variables. So I should say that. And then notice that we still have coefficients just like we did in simple linear regression. So this should really look like an extension of simple linear regression. We have what we called the intercept or constant. Then we had what we called the slope before, but it's the coefficient with x1. We have a coefficient with x2 all the way up to a coefficient with xp, that is beta sub p. And I'm writing this right now in terms of the population model. If we change those betas to b, then we're talking about a sample. And then, of course, we have the part that's not explained, and that is the residual. So this forms our linear regression model. The trick is trying to find values of b when we use our sample data, trying to find values of b that will minimize those residuals. Remember that when we do simple linear regression, it's often called least squares regression, because what we're trying to do is we're trying to minimize the squares of the residuals summed together. There is no way to put a line through the points that minimizes the distance to every single point. So we want to minimize the distance over all the points. And the way we do that is try to minimize this residual. And not a single residual, but a combination of those. Remember, if you start adding up residuals, negatives and positives will offset each other. So we square them, and we try to minimize that sum of squares error. That is, that the squared residuals all added up. So that's the goal. Now, fortunately, we don't have to do the mathematical calculations to be able to minimize this. We actually can let R do it for us when we run the computer, but there are mathematical formulas that would give us the minimum, the values for each of the coefficients that will minimize the sum of squares error. But we're not going to worry about that. We're just going to let our computer program do it for us. Each weight, that is each coefficient, identifies the change in the response variable for every unit change in the explanatory variable while holding the other variables constant. Now, when we did simple regression, we did not have this part because there were no other variables. But now with multiple regression, we actually have to think about the interpretation of a coefficient like beta 1. That's the change in the response variable, and in fact, it is average change because we're not talking about the coefficient as this works the same for every single participant in our study or every single unit we're analyzing. That's the average change that we have there for every unit change in the explanatory variable. Okay, so, and while holding other variables constant. In other words, think of it as a science experiment. If you were going to conduct an experiment in which you wanted to see how far the ball will roll when you roll the bar on the smooth surface you've created for this experiment, what are you going to do? You're going to make sure that every time you use the roll the ball, if you're studying, for instance, how far it will roll on different surfaces, you want to use the same force every time. You might want the temperature to be the same. That is, you're going to want to hold all the variables constant except the one you're focusing on. And that's the way it is here. When we're focusing on x1, what we're looking at with beta 1 is how much change we have if we could hold all those other variables constant, how much a change we would get in y for on average, for every unit change in x1. So you're hearing the same kind of words you heard me talk about with simple linear regression, except now we're doing it with more variables. So let's go ahead and hop over to our report that we're working on. And in this report we're working on, let's try out some individual models and see what we can learn from those models. So the first model I'm going to go ahead and try, I'm going to call it the full model. I need to be doing this in an R code chunk, or we won't get anywhere. I'm going to call this the full model. And this full model, what I mean by full model is that I'm actually going to look at the doctors, the number of physicians, as a function of all the other variables I have here, and there are 3 of them. So I am going to look at doctors as a function. There's LM for my linear model. I'm going to look at doctors as a function of all the other variables. So that's hospital beds, that's income, that's density. Okay, that will give me my full model. If I run this, nothing shows up because I stored it over here in full model, but we do see that there is a full model and there's a bunch of stuff stored in the full model. So as we learned with simple linear regression, we can see more information by getting a summary of our model. So I'm going to get a summary of the full model, and here's my summary. All right, so here are there are the residuals. We've talked about that before. They range from a prediction being off by 55 on one end to a prediction being off by 98 on the other end. I don't know what the relative amount is of that until I start studying the overall model, and we'll talk about that in a little bit. But first of all, let's make sure that we can capture our actual linear regression model out of this. These estimates here, these are the coefficients. These are the coefficients that make up our particular model. So let's go ahead and actually, to make sure that we understand this, let's go ahead and actually write down that model. And so I am predicting that I'll go ahead and use rather than the variables. I'll go ahead, or rather than y's and x's, I'll use as the variables the actual names we're using up here. So we are estimating doctors. I'll put a little hat on that to say that we're estimating. We are calculating a prediction or an estimate of the number of doctors per 100,000 people in the town as my constant, which is listed here as intercept, is minus 39.7. And then I have for hospital beds plus 0.035 beds. I'll just put beds. Plus I have 15.6 income. And of course, beds is per 100,000, income is 1,000. It's per capita income, $1,000. Income plus or minus 0.11 density. So that's the equation. That's what I get for a prediction for doctors. And I just realized I've not been showing you what I was writing, so there it is. Okay, so you heard me writing, but now you see what I wrote. So doctors is equal to minus 39.7 plus 0.035 beds. So all those estimates are coming from right here. We can see that peeking out here on the left side. Plus 15.6 times income minus 0.11 density. Okay, so that's our actual regression equation that we have here. Now, looking further at those coefficients, let's notice a couple things. First of all, if I focus on, we never bother by focusing on that constant. The constant is simply there based upon where our actual data range is located. So I'm just not going to focus. We need it in the equation, but we never think about do we remove it or don't. We always keep it in. So I'm not going to touch that. But let's look at these other variables. So if I look at hospital beds, not just at the estimate, but at the standard error that I have here, the standard error, and then if I take a ratio of those, the estimate to the standard error, remember standard error is the variance of our statistic. Okay? Think about sampling distributions of this time, not means, but regression coefficients. So you probably are used to sampling distributions of means, but now we have sampling distribution of regression coefficients because you can create a sampling distribution of any kind of statistic. And those regression coefficients all have variability. Furthermore, since we have more than one regression coefficient, they all have different variability. And so we have a standard error, which is an estimate of the standard deviation of the statistic. And that estimate is 0.0140. And then if we were to take 0.03515 divided by 0.0140 and put it in this ratio, sorry, I did not give the extra zero there, 315. Okay, now try it. There we go. Then we end up with our t-statistic. And our t-statistic can be compared to a t-distribution. And when we compare it to a t-distribution, we get a p-value of 0.01. And that should sound to you pretty small. What does that tell me? That tells me that my estimate is actually pretty stable relative to, based on the standard error that I actually have for that estimate. Based upon the variability of that estimate, It is large enough for me to be able to say, yes, estimate is adding something to this equation. So I'm looking at that and I'm saying that's making a contribution. Similarly, income's making a contribution. But what I also see down here is that density has a standard error that's so big relative to the estimate. In fact, it's almost the same. Notice this is about 0.1 and the estimate's about 0.1, that I end up with a t-value of about 1, and that actually has a fairly large p-value of 0.28. So in this particular model, density is not very stable, and I'm concerned about it from sample to sample to sample. I'm also concerned about whether it's making a meaningful contribution in this particular study. Now, you might ask the question, should I look at all of these and just take all the values that are under 0.05? Typically, we don't do that in regression. I know it might make sense from your past experiences with inference that why wouldn't we just go ahead and use 0.05? And there are some people that do that, but most folk who work in regression analysis just look to see if the p-value is reasonably small, something close to 0.05, that there's enough stability in the presence of the other variables to be able to say it's making a contribution. And the only one here that I would call into question would be that density. You may recall that when we looked at the zero-order coefficients, that density had very little correlation, almost no correlation with doctors, and you might say, aha, so there I expected that. But here's the problem with that thinking. Variables are correlated with each other as well. And because they're correlated with each other, a variable that is uncorrelated with the response when you look at it by itself can become correlated with the response in the presence of other variables. So it's very difficult to determine by looking at zero-order correlations what's going to happen. Now, you might have heard me say, oh, I predict that it's not going to do much. Let me explain my reasoning. Not only was density not related much to doctors, it wasn't related much to hospital beds and income. And therefore, I expected that in the presence of hospital beds and income, they would not change the relationship of density with doctors very much. And in fact, that does seem to be the case because density doesn't make much of a contribution in our formula. But be aware that you might have situations where you have a zero-order correlation near zero, but the zero-order correlation of that same variable with the other explanatory variables might be quite high. And as a consequence, you might end up finding that a variable that you don't think is going to make a contribution in the model does make a contribution in the presence of some of those other variables because of its relationship with those other variables. Multiple regression can be very difficult to predict what's going to happen until you actually look at the results of the model. Now remember, my first statement about multiple regression was I would prefer that we build a theoretical model and then test it out to see how it's doing. And if I had chosen those three variables on the basis of theory to be my explanatory variables, and I look at this, I would say, theoretically, I expected density to actually be making a contribution as well. Why is it not? But I wouldn't throw out density on the basis of the p-value. I would rather think about whether theoretically I need to keep it in there or go back and study my theory some more. So it's not easy. Science is hard, but this is what we get in this particular case. I am going to throw it out because we are doing exploratory analysis, and I'd like a parsimonious model, meaning as simple as I can find and still explain a lot. So What I'm going to do in the next video is look at other models and then start talking about how we can compare these models to one another as we explore to see which models are performing well and which may not be performing as well.